à Braunschweig et il travaille sur la mécanique des solides théoriques et computationnels, disons. Et bon, c'est aussi un jour particulier pour les Italiens, car c'est le 25 avril, c'est le jour de la libération en Italie. Et donc c'est un jour férié des fascistes. Bon, on en discute parce qu'il y a aussi... Oui, il y a encore les fascistes. Ouais. Mais c'est pour ça, qu'il faut se rappeler. C'est pas la chute de Mussolini, mais oui, c'est les jours où on fête la libération de l'Italie, où je crois à Rome a été libérée.
Ouais.
Donc, je laisse la parole à Laura qui nous parlera des modèles de type champ de phase, donc régularisés pour la rupture et la fatigue.
Thank you very much, Corrado. Should I switch something on here, or is it okay? Good morning, no ladies. Good morning, gentlemen. First of all, I would like to say that I'm really enjoying this day in Paris, and I would like to say thank you to Corrado for hosting me in such a wonderful way. My French is more or less enough to order stuff at the restaurant, but certainly not to have a seminar, so I will be talking in English, as you can imagine. And I will be share with you some results from my group on phase field computations of fracture and fatigue. There are a number of people who have contributed to what I'll be showing, but the list is at the end, so I will show you all the names at the end. So first of all, an outline. Corrado said that not everybody here are really familiar with the phase field approach to fracture, so I will introduce the approach. Then I will go through a quick overview of what we have been doing in this field in the past few years in my group. And then I will talk a little bit more about some recent extension that we are developing still, the extension to fatigue in the same framework. And finally, I'll draw a few conclusions and show a short outlook. So, computational fracture mechanics has a lot of possibilities. I'm not listing all of them by any means. I'm just listing some popular approaches. Remeshing is a possibility in the finite element setting. You have some thresholds. As soon as the threshold is met, you disconnect nodes and so have criteria for crack advancement. You need, of course, a lot of criteria. You need criteria anytime two cracks want to merge in one, or one crack wants to split. You need criteria for the direction of the crack and so forth. And also you need projections between different meshes if you have history variables, for instance in plasticity, or if you have other types of complex material models. GFEM, XFEM, so generalized finite elements or extended finite elements are also quite popular choice. In this case, you don't need the crack to go between elements. You can have enrichment within one element. You can allow for jump in displacements. Also in this case, you need criteria pretty much for any complicated topology of cracking. If you want, again, branching or merging of cracks, you need ad hoc criteria for that. And also, if I may, integration and conditioning are big issues, and coding in 3D is very, very complicated. So I really wouldn't like to be the one coding this in 3D. There are people who do it, but it's not really something that one finds very comfortable, at least. Cohesive zone modeling is also very popular. It's certainly a very good choice if you know in advance where the crack is going. For instance, if you have B-material interfaces and know that the crack is propagating at that interface. But there are issues if you don't know. In many times you don't know upfront where the crack is going. In this case, it might be difficult to apply this approach. And then there is a big family of damage approaches, and what we call phase field approach to fracture is actually one special category of damage approach. But not all types of damage approaches are really have all the features we desire. For instance, there are categories of damage approaches where the damage pattern, which you can then consider to be an indicator of where the crack is going, gets fatter and fatter as the load progresses instead of propagating. So there are so many approaches there that it's difficult to classify which ones are have really desirable features and which not. So what do we mean when we say the phase field approach to brittle fracture? Because so far, in all this talk, I'll be concentrating about brittle fracture. Now, the subtitle could be Fracture Mechanics Problems Solved through PDEs, because as opposed to what the other methods are doing, here we will be solving PDEs, which will tell us automatically where the cracks will be running. So if we go back to the very old approach by Griffiths, this is a very simple energy-based approach that we all learn in undergraduate classes. If we call psi the elastic strain energy, then what Griffiths is saying is postulating that we have already a pre-existing defect or pre-existing crack in the structure, and the initial length of this crack is called A. Now, if the crack propagates by an amount dA, on one side there will be a release of elastic energy, and on the other side there will be the need for a supply of additional energy to create the additional surface of the dA, of the propagating crack. So what Griffith is saying is that the propagation is possible when the so-called critical conditions are met, when the release of elastic energy due to dA is equal to the supply of surface energy needed for this dA, and this supply of surface energy per unit length in 2D or surface in 3D of the crack is what we postulate to be a material property that we call GC, so the fracture toughness of the material, or the critical energy release rate, or the fracture energy, or so forth. Different books or papers use different terminology. Then at the end of the 90s, Jules Francfort and Jean-Jacques Marigot, whom who's probably very well known here, devised the variational approach to fracture. They basically recasted Griffith's problem in the form of the minimization of an energy functional. Now, this energy functional has two arguments. One is U, the displacement field, and the other one is gamma, the crack set itself. So the energy functional is the sum of two terms. One term is the integral over the domain of the elastic strain energy density, and the other term is the integral over the crack set of the fracture energy. And since we postulated this to be proportional to GC, this is simply equal to the GC times the integral over gamma of the gamma. Now, the minimization problem of this functional is a very tricky problem to be tackled, especially in the numerical setting. It's very hard to solve this minimization problem, and so a very important step forward was made shortly after by Bourdin, Francfort, and Marigot again, where they devised a regularized version of this functional. Interestingly, a similar problem had been tackled in the image processing community, where a similar functional had been introduced by Mumford and Shah, and the regularization of this functional had been also pursued by Ambrosio Tortorelli and other researchers. Yeah. The first paper, yes, but I believe the application to this functional came later. But yeah, but the original works date back. Yes. Because the original problem was scalar, no? So in the image processing, and this is then with the vector here. So in this functional, you see that now we have again two arguments. One is the displacement field as before. The other one is what we call the phase field, but you can also think of it as a damage variable. I actually like to think of it as a damage variable. That's why I like to call it D. The first integral is again the elastic strain energy, but now you see that we have a function that we call the degradation function, G of D, which is basically degrading the elastic properties of the material as the damage is progressing. And the second integral is, as opposed to before, now again a volume integral. And it's a regularization of the previous integral over the crack set. So in this integral, you see that we have on one side we have W of D, which is a damage dissipation function. I'll show you in a second what these functions all can look like. And also importantly, we have a gradient term. So you can think of, in fact, of the problem of minimizing this function functional as a gradient damage approach, in a sense a special category of gradient damage approach. And we all know most likely that without a gradient regularization, a local damage approach would be ill-posed. So there would be a mesh sensitivity where as you refine the mesh, the dissipated energy due to damage decreases to 0. So if you have an infinitely fine mesh, you don't dissipate anything. This because you have localization on a band of with one element in the finite element implementation. So as soon as you introduce a gradient, the gradient of D, then of course you have a length scale coming into the picture. This is indicated there as L. And L is a very important parameter in this model. There is a very important mathematical property that if L tends to 0, then you have the so-called gamma convergence property. So minima and minimizers of this functional converge to the minima and minimizer of the previous functional, the unregularized one. And these results are due to the mathematics community, among others, Ambrosio, Tortorelli, Brides, and so forth. Another thing I haven't said about D is that D must be constrained to be between 0 and 1. D equal to 0 means intact material, no damage. D equal to 1 means fully damaged material. And so basically what we want to do is to minimize this functional, and through this minimization, this constrained minimization, we want to find out what U and D are. Now, just to give you a sense, what functions are often used for the degradation function G of D and for the damage dissipation function W of D, there are several options. The group of Jean-Jacques Marigot has shown, including Corrado also, they showed many consequences of the choice of one function or another. For instance, if you use D here, you have an elastic limit below which no damage occurs. If you choose D square, you find out that there is no elastic limit, so you start damaging from at 0 load and so forth. So the choice of one or the other is not arbitrary in a sense. Now, I haven't told you the entire story, because if you use this functional and minimize this functional, what happens is that you're not seeing whether you have tension or compression. So basically, if you have a situation under compression, you would still crack your material. So you're not really distinguishing. And of course, this can lead to physical results in some cases where, for instance, compression is dominant, or when you have shear, so that you have then principal stresses of tension and compression. Now, so in some sense, you want to split your elastic strain energy in two portions. One portion you want to be responsible for damage or cracking, and the other portion you want to be transparent, let's say, to cracking. Now, how you do this is certainly not immediate. But there have been different choices proposed in the literature. So basically, yeah, these three papers proposed, first of which is also co-authored by Corrado. They proposed a volumetric deviatoric split. Then Mie and co-workers, they proposed a spectral split. Freddi and Roya Carfani proposed yet another. So there are still other proposals coming into the picture, because none of these splits is perfect in every situation. But in any event, this I think was worth mentioning. And finally, an important ingredient of the formulation is that if you think of D as a damage variable, you would like damage not to heal. So you would like your damage to be able only to increase. So in this sense, that minimization there is constrained, because you constrain the minimization to only increasing damage variable. Now, this is, let's say, a graphical interpretation of the regularization through this parameter L. So if you have a propagating crack that you want to describe through the phase field, what will happen is that you will have a very steeply varying phase field D, which will be equal to 0 wherever the material is intact, and will steeply vary between 0 and 1 in the vicinity of what you consider to be the crack. So basically, D will be equal to 1 if you you wanted the axis of the crack. And the width of this smeared approximation of the crack, in a sense, is proportional to L. So the smaller L, the closer your smeared crack approaches the, let's say, sharp crack that you would like to approximate. And so this is a very immediate interpretation. Of course, you can also understand within numerical methods, such as the finite element method, if you want to resolve such a steep variation, you need fine elements. So the elements must be fine enough to resolve this variation. So the smaller L, the finer the mesh that you need to use. Now, so this is the energy functional. I'm just repeating it here. Imagine that we have body loads, traction forces. So in general, the total energy will include also these contributions. Then we want to minimize this functional, and this leads to the governing equations of our problem in strong form first. Then, of course, you need to derive the weak form for the finite element formulation and so forth, and discretize. Now, the mechanical problem looks like that. It's a standard divergence of sigma plus p equal to 0, where, however, sigma now contains the degradation function g of d, which will affect the elastic properties as the damage progresses. And then you have standard boundary conditions, Dirichlet and Neumann. Regarding the phase field evolution is dictated by these three equations, or two inequalities and one equality. So in Kuhn-Tucker form, if you want. So you have a damage domain, a damage threshold condition, and then you have the irreversibility condition, and then you have a consistency condition, which corresponds, if you want, to energy balance in a sense. Plus you have homogeneous Neumann boundary conditions on the entire boundary of the domain. So this is the resulting problem. It's a coupled problem, and typically this is solved through a staggered solution scheme. Why? If you try to solve this problem monolithically, so if you want to solve simultaneously for U and for D, what happens is that you get no iterative convergence. And the reason is that this functional is non-convex with respect to both arguments at the same time. But the good news is that if you freeze D and solve for U, or if you solve U and solve for D, then you have no such issue, because with respect to each argument separately, the functional is convex. And so this is why an alternate minimization, as it is also called, or staggered scheme, as I typically call it, is unproblematic. It will always lead to good results. So now, if we place this approach in the context of the previous other approaches, what are the advantages? Well, in my view, the most important advantage is the flexibility. So you basically need no ad hoc criteria. If you want to have an arbitrarily complex crack topology, if you want to have thousands of cracks possibly merging or branching, you don't need any extra criterion, any ad hoc criterion, any additional ingredient. Everything comes out naturally from the solution of the PDEs that we just saw. And you can do this on a fixed mesh. Of course, this is not really very efficient. You would like to refine where the phase field is evolving, but theoretically you can do this also if you want on a fixed mesh. You can do it in 3D in a straightforward fashion. And the disadvantages is, of course, that you have this steep variation of the phase field, so you need a very fine mesh, at least there where the phase field is evolving. And solution procedures still need some care because of the non-convexity of the functional, which may lead to some problems. But just to show you that this approach can be used also for very large problems, I'm showing you the last large problem that we have been solving in my group. This is a specimen of concrete that comes out from a CT, from a computer tomograph. So this is the real geometry. The contrast is not very good in the image, but here you can see aggregates, cement paste, pores. These are all resolved, and then with this, with the phase field applied to the cement paste, you can really find very complex crack pattern, which we can observe in the tomograph and at the same time predict with the simulations. And these are simulations with more or less 500 million degrees of freedom, so they are quite heavy simulations. Now, quick overview of what we've been doing in this field in the past years. We've been concentrating, let's say, in three areas. On the other hand, on the one hand, as I showed you, the approach was born for brittle fracture. We've been trying to extend it to more complicated situations and to multi-field models. I'll give you more details in a second. On the other hand, we've been trying to improve the numerics, especially trying to address the issues on robustness of computations, as I was mentioning before. And then also we've been trying to combine the approach with structural elements, so with, for instance, shell kinematics, so that it would become less expensive to run fracture computations for thin structures. So, for instance, in the field of trying to go beyond brittle fracture, we started by working at ductile fracture. I'm sure there is a lot to be done there. We've been discussing with Corrado about this a little bit. We coupled also the problem of fracture of the solid with the problem of transport of fluid in a porous medium. So, in a sense, we coupled the phase field theory to the theory of porous media to analyze especially desiccation problems in partially saturated materials. We are studying fracture in concrete within a priority program of the DFG in Germany. We've been doing the first steps towards fracture in anisotropic materials, but this is still an area where we have a lot more to do. And then recently we extended the approach to fatigue, which is what I will be dealing with in the next part of my talk. So this I will cover more in detail. And then on the side of improving the numerics, we've been trying to devise a monolithic approach to the couple problem of solving for U and for D. As I said, this is not easy because of the non-convexity of the functional. So what we've been trying to come up with is a spatial line search, which acts in a sense as a safeguard algorithm against a catastrophic divergence. Because if you do nothing, a monolithic minimization approach will catastrophically diverge. So with this spatial line search, we've been able to safeguard our iterative scheme from this catastrophic divergence. When we published the paper, we were actually quite happy about how this was performing. Afterwards, we found out that there was another example where we have some stagnation issues, so that is still not perfect, but I think that is something where more can be done. Then we've been working on adaptive mesh refinement and on fracture within the finite cell method. That is a quite popular method for engineers when you have very complicated shapes and you want embedded type of domain discretizations without having to resolve all the features with, for instance, multiple materials or holes and so forth. And then recently we have also combined the approach with non-intrusive local global coupling algorithms to enable also in the industrial setting with complicated meshes that come from commercial softwares, the application of this technique. And then the contribution on structural mechanics, in a sense, we combined the approach with the solid shells. That was actually not a problem because solid shells, in a sense, are like solid elements with some remedy against locking. But we also combined a little bit more tricky was the combination with Kirchhoff-Love shell kinematics because of the split that I was mentioning. Because in that case, of course, you have a linearly varying strain along the thickness. You want the fracture to happen as a result of the tensile stresses and not the compressive stresses. And at the same time, you would like to have one phase field for the midplane because you have all your degrees of freedom on the midplane. And so reconciling these opposite, let's say, desires was not completely easy. But in the end, we were quite satisfied with the results. And right now, we are extending this to Reisner-Mindlin shells more or less along the same lines. So now, regarding fatigue, I promise to go more in detail about this recent extension. what are the ingredients of this fatigue extension? Well, first of all, we need a variable that tells us what is the mileage of the material, so how strong the fatigue effect is. So we need a cumulated variable that we treat as an internal variable, and I'm putting it there in a very general form. In the beginning, we thought this could be any scalar measure, for instance, of strain or of stress, or for instance, the elastic strain energy density. But I'll show you very soon that not any of these choices is good. And in particular, I'll show you that out of these three options that I'm writing there as examples, only the second and the third are possible choices, and the first one is not good. Then we also want a distinction between loading and unloading. So if you consider an easy one-dimensional situation where you have an epsilon, one-dimensional strain that is varying sinusoidally over time, you want only the blue portions of the history to accumulate your fatigue variable, because those are the loading phases, and many experiments have shown during unloading the fatigue effect is not there. So you need some condition for accumulating your variable only during the loading phases, and possibly you want to account for this tension compression asymmetry that I was mentioning before. So possibly you don't want to accumulate everything, you only want to accumulate the portion of the strains or stresses or elastic strain energy, depending on what you choose for accumulating variable, which you consider responsible for damage, consistently with what you use as split in your formulation. It can be a volumetric deviatoric split or any other type. So possibly you may also want to account for the so-called mean effect. It's known from experiments that if you have a given cycle, not only it's important how let's say how big the amplitude of this cycle is, but also how high the average value of the cycle is. And if you want to account for this, you need to introduce your alpha, not only the alpha dot in the integral, and so. But this is, let's say, an option that we have not really used in our computations yet. So this was the first ingredient, the accumulated variable. Then you need a fatigue degradation function that is responsible for reducing, as I'll show you in a second, the fracture toughness of the material. This is the approach that we are following. We consider fatigue effectively as a degradation of the fracture toughness, and the degradation of the fracture toughness is performed through this fatigue degradation function. Now, of course, this function must satisfy some requirements. We want this function to be equal to 1 if the accumulated variable is less than a given threshold, because we assume that below a given threshold there will be no fatigue effect. This again comes from the phenomenology, from the experiments. We want, of course, the function to be positive and to decrease, and to be always between 0 and 1. So simple choices are shown here. The first choice is decreasing asymptotically to 0 as the accumulated variable increases. The second choice decreases up to 0 for a finite value of the accumulated variable. And then the third choice has the so-called fatigue threshold, which means that if the accumulated variable becomes larger than a given upper threshold, then there is no degradation anymore. This might be used to account for materials that show infinite life if the amplitude of the applied stresses is low enough. Although recently there has been a lot of work on ultra high cycle fatigue, it has been shown now that people are running not only the 2 million cycles that had been run in the past, but also 10 million and 20 million cycles, that maybe this effect is not really present, but there is really a degradation. But this, of course, is also material dependent and case dependent. So these are the choices that we've been using in our computations. We've been doing most of the work with the first choice, just because so far we have no reason to prefer one or the other, but we are right now in the process of comparing results of this approach with real experiments, so that we will be able hopefully to say something more soon. So then, how do we modify our formulation? What we have is now a modified energy functional where the dissipation, of course, becomes history dependent. So we need to introduce this fatigue degradation function inside the damage part of the integral, and we need to account for the history. So effectively what happens is that this degradation function multiplies the fracture toughness, and so we have a degraded fracture toughness over time, and also we have an additional term that contains the gradient of this function, scalar the gradient of the damage variable or phase field, as you want. So with these relatively minor modifications to the approach, then we can account for fatigue. Now let me show you the first results that we got. Now this is a very classical single edge notch tension test. If we run a monotonic test of this specimen, then we get a very brittle behavior. This is the force displacement curve. You see that the behavior is mesh independent, as it should be. And what I'll be showing now is what happens if we cycle the specimen at a level that corresponds more or less to half of the maximum force or maximum applied displacement under monotonic conditions. So we'll be applying cycles of that shape, so linear cycles, and what will happen is that the basic effect is that as the alpha bar is cumulating, then f of alpha bar is decreasing, so the fracture toughness is decreasing, and so the crack will continue propagating over time due to the fatigue effect. So this is, let's say, the basic feature that we wanted to reproduce. But then the first check we made was mesh insensitivity, and we found out, perhaps not surprisingly, but at the beginning we hadn't thought about this, that if we use as cumulated variable some norm of the strain tensor, since the strain is still singular, then of course what we get will depend on the mesh. So choosing as cumulated variable a strain measure is not good, because of course as you refine, your mesh is finer and finer, you capture a singularity better and better, and so you get a faster and faster accumulation of alpha, and therefore your fatigue effect becomes stronger and stronger, and in the limit you get an instantaneous propagation of the crack due to fatigue. But if you use, for instance, as we did, the degraded positive part of the elastic strain energy density, this is a good option, then results are mesh insensitive. So you see here, okay, the first mesh is still too coarse, but the second and third are on top of each other, the results. Another, I'm sure one could also use the stress, some measure of the stress which contains G of D, and so is also not singular. Then the next objective was to check if this approach, that in fact is a regularization of Griffiths' approach, can be used to predict Paris law, which is also based on a linear elastic fracture mechanics background. So in theory, we expected to be able to recover Paris law. And to do this, we chose a very typical type of specimen, the compact tension test that has an ASTM norm, so we follow the norm. And for this ASTM norm, we know exactly how to compute delta K. Delta K would be, for a cycle, the amplitude of the stress intensity factor during the cycle. And of course, during cycling, we are updating also the length of the crack, so that it's so delta K is computed always on the current crack length. And so what we want to see is if we can recover the expected behavior with this approach. What is the expected behavior? Paris took a lot of experiments on fatigue, and he plotted on the x-axis the logarithm of delta K. So the amplitude of the stress intensity factor along the cycles. And on the y-axis, he put the logarithm of dAdn, so the rate of propagation of the crack with the number of cycles. And what he found out is that there is an initial phase that corresponds to nucleation, there is a final phase that corresponds to failure, and on these phases there is not so much to be said because these are both case-dependent, geometry-dependent, and so you cannot say anything general on those phases. But in the middle, there is a stable crack propagation phase, which obeys in the log-log plane a fairly linear law, yeah, which is known as Paris law. So dAdn is basically given by c times delta k to the power m, where c and m are two parameters that are only material dependent. So if you run experiments with different setups, you find the same c and m, because these are parameters related to a local behavior which is condensed in the information given by delta k, which is a local quantity, the stress intensity factor. So, and what we found out with our numerical experiments with the same type of, with the compact tension specimen, is that the behavior really resembles what we expect based on Paris. So if we change, of course you can get the same delta k in different ways. You can get the same delta k depends on P, on the applied load, it depends on the crack length, and depends on the geometry. In this case the geometry is fixed, but we change the initial crack length and we change the applied load to recover the same delta k, and we found out that all the possible choices that we made led to different initiation branches and different failure phase branches, but the middle range is given by a fairly linear law where we can basically identify C and M based on numerical results instead of experiments. Of course, assuming that we have first identified our fatigue degradation function, which is basically what we need to identify through the comparison. So we were pretty happy about this. Now, another feature of behavior of fatigue that we wanted to recover is the oldest information on fatigue that was available to the engineers already in the 1800s, the so-called Wöhler's curves. These are curves that are, as opposed to Paris results, these are case dependent, so specimen dependent. Here you have the number of cycles on the x-axis and the amplitude of the stress, the applied stress on the y-axis. And what you expect is that, of course, if you have only one cycle, then what you find there is that you can apply at the maximum the tensile strength, the static strength of the material in a monotonic test, and as you increase the number of cycles, or as you decrease the applied stress in cycles, then you can sustain more and more cycles, until in some materials you can have some fatigue threshold where if the stress is smaller than this threshold, then you can have infinite fatigue life. But as I said, this has been also updated in recent times. So now our experiments, numerical experiments, both with CT, so compact tension, and with 3-point bending specimens, show a behavior that is very close to what I just showed you. So we have, if we apply very large loads, what we get is we can sustain a limited number of cycles, and this is the area that we call damage dominated, in the sense that this area is static damage dominated. So the stable crack propagation phase, the central portion of Paris curve, is very, very limited because the stress is so high that you get failure very, very soon. But if you apply smaller loads, so you are in this area, so this is the area that we call fatigue dominated, meaning that you have a fairly large Paris domain, so a very large fatigue stable crack propagation phase. And what we don't have is this final part, and the reason is very simple, because computations are very, very expensive, because so far we've been running every single cycle, and so but we are working right now. I'll tell you something more in a few slides on some multi-scale approaches in time, so that we can we don't have to analyze every single cycle, because this is so expensive that it's very, very hard to then go ahead and analyze the second part of the S-curve. Euler curves are also called S-curves. Now, to conclude, I just would like to show you that the beauty of this approach is that you can not only analyze compact tension specimen. This is something that you could do also with the standard approaches available already, but with the phase field approach, due to its flexibility, you can analyze, for instance, fatigue in complicated geometries where you have multiple cracks intersecting and branching, and also you can analyze, for instance, in this case, a 3D machine piece where you have fatigue effects that start in one part and then continue in another part. So all the approaches in which you have several cracks, for this type of approach, Paris, let's say all the standard computational methods based on Paris law or based in general on linear elastic fraction mechanics are very difficult to apply, because you should compute the stress intensity factor in any tip of any crack is influenced by all the other cracks. So this would be unfeasible, and instead with this approach you can easily do this. So then, as conclusions, regarding especially this fatigue part, the phase field approach to brittle fracture has been extended to fatigue. The new model recovers what is known about fatigue in terms of Euler curves, Paris law. What I didn't show you is that we also found out that the model can recover in the simple cases where the so-called Palmgren-Minor law is applicable. The model recovers also Palmgren-Minor's law. Naturally, without any extra ingredient. It can, in addition to Paris law, which only covers the stable crack propagation phase, this approach can also reproduce nucleation and also final failure, which are specimen dependent, and is able to handle arbitrarily complex geometries, loading conditions, and crack topologies. And right now we are very focused on experimental validation, calibration first, because of course we need to calibrate. We don't need to calibrate CNM as people typically do with experiments, but we need to calibrate our fatigue degradation function. So what we are trying to do now is to have sets of experiments where we can independently get first of all, the standard material properties, so K1C, from which we can also compute GC, and then tensile strength, so that we can calibrate L based on the monotonic test, and then the fatigue degradation function should be calibrated to match, for instance, Paris curve, and then we can independently validate with the SN curve, or vice versa. But in a sense, this is now our current working goal, and here we have a cooperation with NTNU in Trondheim, where there is a group that is very focused on fatigue from the experimental point of view. So they're running experiments for us for brittle materials, which is also not that easy, because the majority of the experimental results you find on fatigue are for metals, and metals are not always brittle enough that you can think of applying this theory. That's why also at the same time we would like to extend the approach to plasticity. And also we are working, as I said, at multi-scale approaches in time, or actually the easiest version would be cycle jump techniques, so that you don't have to resolve every single cycle. And the next step, I think, once this is clear, I think it would be the objection that sometimes people have when I present this, especially material scientists. I had a presentation at NTNU when I visited the experimental group, and some material scientists were in the audience, and they told me, well, you're degrading the GC, but in fact for us, fatigue is not that the GC is degrading, it's that microscopically something is happening so that the demand on the material is increasing. So it's not that the material is becomes less tough, but it's the demand on it that is increasing. This is, of course, another view of the problem, which is not very practical, let's say, for the computation, from the computation standpoint, right? Because our view here is a macroscopic view. We ignore what happens microscopically, but perhaps it would be interesting to connect the two worlds and say, now maybe we can analyze the real microstructure and account for the mechanisms that lead to this fatigue effect, and then maybe derive the fatigue degradation function based on what is happening in reality at the microstructural level. So this might be a possible extension, certainly not short term, but mid-term, let's say. And finally, but not last but not least, I would like to mention all the people that have contributed to all this work over the past years. Maredi Ambati, Tuanica Giui, Pietro Carrara, Claudio Gavagnin, Timothy Gerasimov, Josef Kindle, Roland Kruse, Sindhu Nagaraya. They're all at IAM, at least at my institute. At least they were. One of them is away. Josef Kindle is now at NTNU, became professor, and all the others are either PhD students or postdocs. The first two were PhD students when they started, and now they're postdoc. And but also there was a lot of external collaboration with Roberto Alessi, whom you probably also know, Pietro Lura, Andrew McBride, and Strang Tajareddy and Lorenzo Sanavia. And this work was funded by the agencies that you see mentioned there. And finally, I'd like to thank you for hosting me, in a sense, together with Corrado here in such a nice way, and also for paying attention even today, where people are still on vacation halfway, for your kind attention to this seminar. Thanks a lot.
Je sais pas si ça marche, mais merci. Thanks a lot, Laura. So also I say that Laura is here for the next month, more or less, till the 15th of May. So if you have any question, please, I will.
Yes, maybe I have two questions. There's something that is intriguing me about the convergence of your approach to Griffith. I agree with you. Griffiths works for an existing crack and the growth of an existing crack. But if you use Griffiths for crack nucleation, as you mentioned in the conclusion, it is known that it gives no answer. It cannot. Griffiths concludes that no crack can nucleate. My question is, in that case, what becomes the convergence?
Yeah, so this is actually very debated in the community. How come that this approach, well, I wish it was my approach, it's Frankfurt and Marigot approach actually, but the brittle formulation. So what happens is that the gradient damage approach, so the regularized Griffith, is richer than Griffith itself. It's richer in the sense that it contains this length scale, which Griffith doesn't have. No? So this length scale, in a sense, makes a little miracle. This little miracle is that this length scale adds some sort of cohesive-like behavior. It's not a real cohesive behavior in the sense that the crack faces are still stress-free. They don't have any residual stress after the crack starts. But the presence of this length scale introduces some let's say, some additional richness. So it was Corrado who showed, it was a PhD thesis by Jean-Jacques, that if you tailor L, you can match the tensile strength of the material. So imagine you have a bar in 1D. If you have this bar in 1D, you can write the differential equation of the phase field in 1D, and you can find the so-called homogeneous solution, where you neglect, let's say, the gradient, and you assume that everything is homogeneous. And you can find a relationship between tensile strength, length scale, elastic modulus, and fracture toughness. And so this gives you a consistent choice of L for cases where you don't have an initial crack, so for cases where you don't have an initial singularity, you can capture nucleation by an appropriate choice of L at a stress that you can control. So basically you have, and the interesting thing is in the expression for this critical stress, as we call it, L is at the denominator. So if L tends to 0, this critical stress tends to infinity, which is exactly what Griffiths was saying. No? He was saying you can apply an infinite stress in a material without a crack. And this is exactly what you recover in the limit case of L tending to 0. But the fact that L cannot be 0 and is not 0 in this approach somehow is giving you this additional richness that allows you to describe nucleation as well.
Okay, thank you. I agree with your answer. I can. Yeah. My second question is how to calibrate L. You either it's a mathematical parameter tuned to get some right convergence,
yeah,
or it's a material parameter.
Yeah.
But in case of a material parameter, I am thinking about that because I'm working on that domain. You know that some experiments are done on micro pillar or micro beams, and in that case, if your L is large, the damage zone will spread all over the specimen.
Yeah, yeah. This is absolutely an interesting question. So, in a sense, L is both. This again was shown in the same thesis I was mentioning before. L is both a material parameter and if I'm saying something wrong, you can correct me, of course. If you have a what happens is that if you have a pre-existing strong singularity, so if you have an initial crack, what Griffith would like, let's say, then you can show that the results are quite insensitive to L. So in that case, you have a real convergence in the sense that if L is small enough, then results don't change with L anymore. But if you don't have a pre-existing singularity, then results are very sensitive to L. And in that case, if you don't have a singularity, that means, you can think of the 1D bar problem, which is a classical problem that you would run in the lab to find out what the tensile strength of your material is. So in my view, if you know what we are doing, for instance, in our computations, whenever we have no pre-existing singularity, we tailor L in such a way that we match the critical stress to the tensile strength of the material. And then, now, the problem is, if you want to use the same L for problems that may have or not have pre-existing singularity. So the approach is typically, at least what we do is, we calibrate L based on the tensile strength. But then, once we have this L, there are two possibilities. Either this L is smaller, is much smaller than the specimen size, then everything is fine. But if L is too large for the specimen size, my personal opinion, we've been debating this in Banff 1 month ago, my personal opinion is that this is a clear indication that your material is not brittle enough that you can study it with this method. So that's my personal opinion, because in the end, brittleness is also a matter of the ratio between the processed zone and the size of the specimen. So in my opinion, if you have a given specimen, a given material, you compute L for it based on this critical stress, and you find out that that L is too large for your specimen size, in my opinion, this is a clear indication of the fact that the specimen where you wanted to study fracture is too small to study fracture as a brittle phenomenon, because your process zone size is comparable to the structural dimensions. What happens sometimes, though, is I saw, for instance, a thesis time ago where they wanted to study concrete, and they computed L based on this critical stress approach, and this L was huge. Yeah. On the other hand, if you consider that in concrete, fracture doesn't happen in the aggregates, but typically happens in the cement matrix, if you calibrate L based on the cement matrix, that is much, much more brittle than concrete as a whole. So then L was dramatically smaller. Of course, that means you need to resolve aggregates and matrix. So, but for me, this is my personal view of the problem. If I find out that L is too large, then for me, that means that the process zone is too large for that specimen. So I can forget about brittle fracture for that.
Thank you. Thank you for your lecture.
Thank you. Actually, I would be interested in talking to you regarding finite fraction mechanics, because I think there might be some points in common.
Yeah, maybe we can continue this afternoon. So I don't know if you have some other questions. Otherwise, yeah, I have maybe a question. If you can put the slide when you have the energy for fatigue and the dependence of GC on the.
Wait.
What seems.
This one?
Yeah. So
or this one?
Yeah, I think that this part should be inside the integral, no? This f. So in the sense that this is dependent on the point.
Yes.
Yeah.
Yes, absolutely. Yeah.
And so, what is quite? I mean, can you justify this thermodynamically? Because what seems quite strange to me is that imagine that you have a very small loading, so you do not have damage at all, and you cycle, you will decrease the toughness in this way.
There is this threshold.
There is a threshold there?
There is a threshold, so that in this fatigue degradation function there is this alpha t. So that is a threshold below which nothing happens. So the function
is this related to the threshold that you have for damage?
You can relate it, or
because the things that you can decrease the material properties without any dissipation away.
No, yeah, but we always connect this to the threshold in the damage. So in this case, actually, some computations were done with the quadratic model, in which case you have damage immediately. But afterwards, we switched completely to the linear model, and in that case, we connect the two. Because so if no damage occurs, there will be also no fatigue degradation.
Okay, thank you. I don't know if you have any other question. Otherwise, I think we can say thanks to.
Thank you.